Good afternoon, ladies and gentlemen. Welcome to the second installment of the BFIT online Calculus 2 lecture series. Today we're going to talk about one of my favorite topics in Calc 2, integration or improper integrals. So first we're going to start with some review. I'm going to integrate 1 over the square root of x from 0 to 4. And I'm also going to integrate over here 1 over x from -1 to 1. So I'm going to start with this one. Step 1 for me is going to be rewriting this as instead of a fraction with a weird radical involved, I'm just going to write this as x to an exponent. We'll use -1/2 for this piece. Split the board in half so I'm not mixing these two up. So you get x to the -1/2. You take the integral of that and you get x to the +1/2 divided by 1/2. I can use a plus c. We're just going to go from 0 to 4. This is the same as 2 square roots of x from 0 to 4. So we'll get 2 square roots of 4 minus 2 square roots of 0. So looks like the answer should be 4. On this one, I will also start by flipping this so that it's x to an exponent instead of, gonna make this x to an exponent instead of a fraction. So the integral of x to the -1 should be natural log of x, from -1 to 1. Interesting little side note about this integral. If we're being extremely pedantic, we should integrate this into the natural log of the absolute value of x, because this function can take on negative values just fine. This function cannot, so if you want to find that area, there should be absolute values involved. So I can evaluate this at -1 and 1. We'll get the natural log of 1 minus the natural log of the absolute value of -1, which looks like 0 minus 0, which is 0. So this is the start of the lesson on improper integrals, and here's the bad news. Both of these are wrong. So I am going to stand here for a minute and allow those of you watching at home to contemplate what has gone wrong with these integrals, why they're incorrect, what mistakes you think I've made, or what aspects of the integrals you think that I have overlooked. If you're still thinking about it, pause the video, continue thinking about it. If you have figured it out, or if you're giving up, stay tuned, because I'm going to talk about it. I'm going to erase this one, we'll come back to it. I want to focus on this one. Here's what's wrong with this integral. If we think about this in terms of areas under curves. 1 over the square root of x looks like this. It has a vertical asymptote here at x equals 0 because this function is undefined at x equals 0. Square root of 0 is 0. Dividing by 0 doesn't work. It's no good. It's not going to work. That's what's wrong with this integral. We're being asked to integrate this thing over a range of x values that is outside the domain of the function. You can't get, if we think back to Riemann sums, like if you're going to make some rectangles in here, find the area of each of these rectangles, use that to get your total area. One of these rectangles is infinitely tall. It's got no height because there is no function value at x equals 0. The function is undefined. It means that it doesn't mean that we can't do this integral. It means that we shouldn't do it like it's a normal, regular, everyday integral. It means that we have to do a couple extra steps to make this integrable because this is an improper integral. The bounds do not match the domain of the function, so we got to do extra bonus stuff. And I will show you now what that extra bonus stuff is. We are integrating from 0 to 4, 1 over the square root of x dx. And we know that this is a problem. 0 is not in the domain of the function, so I cannot take this integral using bounds that include 0. So I'm going to fake it. I'm going to take the integral from, I'll go from a to 4. A is just a placeholder variable value that I made up. And I'm going to take this integral like this, and then I'm going to take the limit as a approaches 0 from the right. So I'm taking the 0 out of this expression. 0 is a problem. It shouldn't be there. It can't be there. It's not in the domain. I'm taking it out of the expression and replacing it with an a, so that I'm going to spend most of this problem ignoring this limit business that I covered up so you couldn't see it. I'm going to ignore that limit business for most of the problem. I'm going to do this integral using a and 4, just like we did it 5 minutes ago. We're going to get the exact same integral. But then instead of plugging in 0, I'm going to plug in a. And then at the very end, I'm going to take the limit as a approaches 0 from the right. Why from the right? Because I'm only interested in what's going on between 0 and 4. I'm going from the right because the rest of this entire region is on the right of 0. I don't care what this does to the left of 0. That's not the region I'm interested in. I'm only interested in coming to 0 from this direction. If I was going from like -4 to 0 up here, then I would approach 0 from the left, because that's where I'm coming from. So, we got a limit. We got bounds that do not explicitly violate the domain of our function. And now we're going to do exactly what we just did 5 minutes ago, but it's going to look pretty because there's a limit involved. So I have the limit as a approaches 0 from the right. Again, first step in actually integrating this is rewriting it as x to the -1/2 instead of 1 over the square root of x. Then we can, I'll go down. The limit as a approaches 0 from the right hangs out. I know that the integral of this is x to the +1/2 divided by 1/2, evaluated at a and 4. limit continues to hang out. The limit is going to hang out this whole time. I'm not going to actually deal with that until the very end. We said that this was actually like 2x to the 1/2. That's how that dividing by 1/2 simplifies. So this is going to be 2 times 4 to the 1/2 minus 2 times a to the 1/2. So aside from this limit, as a approaches 0, instead of a 0 being here, nothing has changed from the first time we did this. And instead of plugging in 0 and finding out that we get 0, we're going to take the limit as a approaches 0, and we're still just going to get 0 here. And this piece is going to be 2 times 2, so turns out we still get 4. So the answer we got to, doing it wrong, was the correct answer. But the process we used was wrong. The process we need to use involves limits, because 0 is not in the domain of this function. So, at this point some of you may be wondering why we need to do all this extra work if we just get the same answer. And the reason is partly pedantry. It's just not correct to plug in 0 to a function that you can't plug in 0 into. Part of this is it's not always going to work like this. There are some examples where once you do it with the limits involved, you're going to get a very different outcome than you would if you just tried to plug in the number. Let's take a look at one of those. The other example I opened with was the integral from -1 to 1, 1 over x dx. And the problem with this is exactly the same problem. It's an issue of domain. 1 over x looks like this, and like this. It still has a vertical asymptote at x equals 0. Now you may be saying, I can plug -1 into this function, that works. I can plug 1 into this function, that works. What's the problem? The problem is that 0 is between these numbers. So when we're integrating from -1 to 1, that means we're getting everything in this range. And at least one thing in this range doesn't make any sense. The integral from -1 to 1 is going to cross through this boundary, and some of the rectangles we're going to use for area in this are not going to exist. So we're going to do something else instead. For the last one, we found the bound that was the problem, and we replaced that bound with a limit of a placeholder. In this one, the bound isn't the problem. The problem happens in between the bounds. So we're going to have to do a little extra work. I'm going to rewrite this first as the integral from -1 to 0, 1 over x dx, plus the integral from 0 to 1 of 1 over x dx. This is taking the region from -1 to 1 and just splitting it into two parts, so that the problem is a bound in each part. Now that the problem is actually the boundary, I can replace it with a limit and continue doing this problem. So this first piece, I'm going to replace the problem boundary with a letter. I always use B for the top bound in these problems, and A for the bottom bound in these problems. And in this one, I need the limit as B approaches 0 from the left. It's coming this way from negative. I should not have erased that thing. So B is going to go to 0 from this direction. A is going to go to 0 from this direction. So A is coming in from the right, B is coming in from the left. They're both headed towards 0. They're going to each affect these integrals separately. So this is the setup step that we do to make this thing integrable, because as originally written, it is improper. I should write that down somewhere. The section is improper integrals, and I'm pretty sure it's section 8.9. We're skipping a big chunk of chapter 8 in the middle there. Is that even showing up on the video? No? How's that? There we go. Nope. Good enough? Okay. So, as originally written, it's an improper integral, so we split it into two so that the problem is a bound on each, and then we replace the problem bounds with placeholders, take the limits as those placeholders approach the problem. So, now we can continue doing these limits these integrals just like normal. I'm going to carry down the limit as b approaches 0 from the left. The integral of 1 over x dx is the natural log of x from -1 to b. This, I'm going to carry down the limit as a approaches 0 from the right. The integral of that is still the natural log of x. This time we're going to go from a to 1. So I get the limit as b approaches 0 from the left of natural log b minus natural log -1. Again, this is absolute value officially. Plus the limit as a approaches 0 from the right of natural log 1 minus natural log a. So now we need to think of what happens as we take the natural log of b and let b approach 0. Natural logs, for those of you that have forgotten, look like this. They have a vertical asymptote here, fx equals 0. And the limit of a natural log, as the argument approaches 0, is -infinity. The closer you get to 0, the more this thing just skyrockets straight downwards. I'm pointing down off camera, trust me. So, this limit is the natural log of b as b approaches 0. This is going to be -infinity. The natural log of 1 is 0. Plus natural log of 1 is still 0. Natural log of a as a approaches 0 is minus -infinity. So the answer so far is -infinity plus infinity. So we should talk about what that means. It's a pretty quick discussion. That means nothing. It's nonsense. Infinities don't cancel. Infinities do not do arithmetic in the traditional way that you would expect them to. If you have infinities trying to interact with other infinities, plan C. You're done. Game over. So we say that this integral diverges. diverges is the official word for the answer to your problem when it's not a number. So the last one we did, where we found that the integral equals 4, we would say that the integral converges to 4. I'm out of places to write that, so you'll have to trust me on that one. First integral we did converges to 4. This integral just diverges. Anytime you do this process and the result is not a number, it diverges. I'm going to cut this first video here before it gets too long. I will be back in the next part of this video with a couple more examples.